Mary Swarnalatha, working as a professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the definitions of multiple random variables. So, what is a random variable? A random variable is nothing but it is generated by capital X. So, a random variable is nothing but assigning a real number to the outcome of an experiment. That is nothing but random variable. Now, define vector random variable. So, what is a vector random variable? A vector random variable is a collection of random numbers with the probabilities assigned to outcomes. It means, for example, if you conduct an experiment, the sample space of that experiment has been represented by S, and it consists of the sample space elements like S1, S2 and so on. Let us say Sn. Now, what is a random variable? Random variable is nothing but what? Assigning real numbers to each outcome in the sample space is called as what? Random variable. Now, what is random vector? So, a random vector is nothing but what? Collection of the random numbers, nothing but x1, x2 and so on, xn. So, a random vector is nothing but what? Collection of random numbers which are nothing but assigning real numbers to the outcomes of that experiment. That is nothing but what? Vector random variable, which is also called as what? Multivariate random variable, which is a collection of what? The random variables. And the next definition is define two-dimensional random variable. So, two-dimensional is nothing but in the sample space S, we are going to define two random variables. Let us say X and Y. So, on the sample space of an experiment, if you are defining two random variables X and Y, then it is called as what? Two-dimensional random variable. And the pair of these two random numbers has been denoted by the X comma Y. So, this is called as what? Two-dimensional random variable. Next one is define joint sample space. So, the sample space is nothing but what? It is nothing but the collection of the outcomes of an experiment is nothing but sample space. Now, what is a joint sample space? Joint sample space represent the combinations of outcomes of two or more uncertain processes is called as what? Joint sample space. For example, I am defining one experiment such that rolling a die. So, when I roll a die, what are the possible outcomes? I am going to get as what? 1, 2, 3, 4, 5, 6. So, let us, this is an experiment. And one more experiment I am connecting is tossing a coin. So, when I toss a coin, what are the possible outcomes are going to get? Head, comma, tail. Now, what is the joint sample space? Nothing but represent the combinations of outcomes of two or more experiments or two or more processes. Nothing but what? Joint sample space. Now, the joint sample space has been given by what? Getting a number on the die and getting a head on the coin, or else getting a number 2 on the die and getting head on the coin. So, like that, this is nothing but what? The combination of these two experiments, the outcomes of these two experiments is called as what? Joint sample space. Next definition is define joint probability distribution function. So, the probability distribution function of a random variable X has been denoted by what? Fx of X. It's nothing but what? The probability such that the random variable X takes the value up to X is nothing but what? The probability distribution function for a single random variable X. Now, what is here? Define joint probability density function. A joint probability distribution function represents a probability distribution function for two or more random variables. So, for a single random variable, we are calling it as what? Probability distribution function, cumulative probability distribution function. If you take more than one random variable, so either two random variables or if you take three random variables and so on up to n random variables. So, if you take more than one random variable, nothing but 2, 3, 4 and so on up to n random variables, then the distribution function of these random variables is called as what? The joint probability distribution function. For example, if you have considered two random variables x and y, the joint probability distribution function of these two random variables has been represented by fxy of x comma y. That is nothing but what? Probability of the joint event such that x takes less than equals to x and y is takes less than equals to y. So this is the definition of the joint probability distribution function. Next one is define two-dimensional discrete random variable. So discrete. So previously has seen the continuous. Now what is my discrete random variable? So we have seen the types of random variables like continuous random variable, discrete random variable and mixed random variable. So what is a continuous random variable? The random variable takes continuous range of values and they are not countable, nothing but what? Continuous random variable. And what is a discrete random variable? A random variable takes discrete instance of values. For example, when I roll a die, what is the outcomes of that experiment? 1, 2, 3, 4, 5, 6. Now on this experiment, I am defining a random variable such that, so whatever the number appears on the die, that should be multiplied by 2. Then what is random variable for that? 1 into 2, nothing but 2. And here 4, 6, 8, 10 and 12. So this is nothing but what? Random variable. If you observe the values of this random variable, they are discrete in nature. They are not continuous. In between 2 and 4, you don't have any values. So it means, what is a discrete random variable? Random variable discrete would consist of discrete range of values. And what is a continuous random variable? A random variable is continuous random variable if the random variable consists of a continuous range of numbers. Nothing but what? Continuous random variable. And what is a mixed random variable? The combination of these two is nothing but what? Mixed random variable. Now this is for a single random variable. The same thing you can define for two random variables also, nothing but define two-dimensional discrete random variable. If the possible values of x and y are finite, are countably infinite, then xy is called as what? Two-dimensional discrete random variable. So if you take a single random variable, these values are countable, like so 1, 2, 3, 4, 5, 6, 7. So they are discrete in nature, they are countable. And similarly, if you take an experiment such that x is nothing but a positive real number, a positive real integer, let us say, then what is x equals to 1, 2, 3, 4 and so on up to infinity. So these values are here discrete in nature, but they are not countable, they are infinite. So what is the two-dimensional discrete random variable? If all the possible values of x and y are either finite or else they are countably infinite, then x and y are called as what? Two-dimensional discrete random variable. So here we have seen the example for single random variable. The same thing can go for two random variables also. And next definition is what? Define marginal probability mass function of random variables x and y. So the joint probability mass function of two discrete random variables x and y is nothing but pxy of x comma y is nothing but p of x equals to x comma y equals to y. So here PMF is nothing but probability mass function. So for two random variables x and y. So how do you denote the probability mass function for two random variables x and y? Nothing but what? Here P represents the probability and xy represents the two random variables x and y of the two values x comma y is nothing but what? Probability of the joint event such that the random variable x takes a specific value small x and the random variable y takes a specific value nothing but small y. So this is called as what? The probability mass function for two discrete random variables x and y. Now what is the next one here? Define the joint probability density function. So what is the probability density function for single random variable x we have seen. So what is the probability density function of a single random variable x? Nothing but fx of x, nothing but the differentiation of the probability distribution function of the random variable x. This is nothing but what? Definition of the probability density function for a single random variable. So here, what is the definition for joint? Joint is nothing but always you have to consider more than one random variable. Then what is the joint probability density function? The joint probability density function nothing but the probability density function for more than one random variable. For more than one random variable and each taking a specific value is called as what? The joint probability density function. So for example, if I take two random variables x and y then the joint density function of those two random variables has been denoted by fxy of x comma y is equals to, if it is a single random variable, differentiation of the distribution function of that random variable. If consider the joint probability density function for two random variables, then it is nothing but the second order differentiation. Because it is two random variables, you have to take the second order differentiation. If it is one random variable, you have to take the first order. If it is two, you have to take the second order. Like that, if it is nth order, n random variables, you have to take the nth order differentiation. So the second order differentiation of the probability, the joint probability distribution function of those two random variables is nothing but what? The joint probability density function. So like that, you can define for up to n random variables also. So the next definition here, what is the area under the joint probability density function? So the area under the joint density function of two random variables x and y is equal to what? Unity. So we have seen the properties of the joint probability density function. So what is that? What is the property of the joint probability density function? The area under the joint density function of two random variables. How do you denote the joint probability density function of two random variables x and y? Then nothing but what? fxy of x comma y. If you consider x and y are continuous random variables. Now, what is the here question? The area. So, area is nothing but how do you calculate the area of this joint probability density function? How many random variables you are having? Two random variables. Therefore, we have to take the double integration. If you want to calculate the area, you have to integrate the joint probability density function with respect to the two random variables, x and y, and that value is equals to what? 1. Then only you can say that it is a proper or valid joint density function. Next one is, what are the properties of joint density function? So what is the first property you have seen already? The area under the joint density function is equals to unity or 1. And the second one is what? It is always a non-negative number. Always the joint density function of two random variables of n random variables is always a non-negative value. And the next one is, how do you convert the joint cumulative probability distribution function into the joint probability density function? How can you obtain the joint probability density function of two random variables? Nothing but fxy of x comma y. And what is the joint area of two random variables? Let us say fxy of x comma y. Here the question is, how do you convert the joint distribution function into the joint density function? How do you convert? By using the second order differentiation. So like that, you can convert the joint distribution function into the joint density function. Next one is, how do you get a joint CDF from the joint PDF? So previously what we have done, we have converted the joint CDF into the joint probability density function. Now what is the question? So from this joint probability density function, you have to convert into the joint distribution function. So what is the joint distribution function of two random variables x and y? Nothing but fxy of x comma y. So here we have taken the differentiation for converting, and for reversing back you have to take the integration. So integration minus infinity x, integration minus infinity y, fxy of x comma y dx into dy. That is the converting the joint PDF into joint distribution function. What is the next one? Define point conditioning. Point conditioning. So what is a point conditioning? The distribution function of random variable x at a given condition, so that the second random variable y has some specific value or a specific point. That is nothing but what? Point conditioning. For example, x and y are two random variables. So the distribution function of, or else if you take the probability. So what is the condition? I am taking here x. So I am taking the here the random variable x, and I am taking the condition on the random variable y. Then the joint distribution function of that random variable such that the random variable, nothing but the conditional random variable takes a specific value, nothing but y equals to y or y equals to yk. If it is taking a specific value, then it is called as what? Point conditioning. Nothing but y equals to what? Yk. So it is called as what? Point conditioning. So next one is define interval conditioning. So what is interval condition? The random variable y has to take a range of values or interval of values. For example, so the random variable y takes the values from y1 to y2. Then this type of conditioning is called as what? Interval conditioning. And the conditional distribution function of the random variable x, and given that the conditioning event, what is conditioning event here? It is taking an interval of values. So this is called as what? Interval condition. This type of conditioning is called as what? Interval conditioning. Next one is define statistical independence of two random variables. So how can you say that two random variables x and y are independent? If and only if the events x less than equals to x and the events y less than equals to y are independent for all the values of x and y. Then you can say that the random variables x and y are statistically independent. That is nothing but what? The joint distribution function of those two random variables is equals to what? Multiplication or the product of the marginal distribution functions of the random variables x and y. Then you can say that the random variables x and y are statistically independent random variables. And similarly, you can also say that the joint probability density function of two random variables is equal to the product of the marginal density function. So these are the conditions for what? Statistically independent random variables. Next one is define density function of sum of random variables. For example, I have taken two random variables x and y, and let us say that these two random variables are statistically independent. If these two are statistically independent, then what is the condition? fxy of x comma y is equals to what? It's nothing but the product of the marginal density functions. Now, you are adding, sum is nothing but what? You have to add, so that you are getting a new random variable z. So, here the question is density function of sum of random variables. So, f z of z is nothing but what? Is equal to what? Convolution of probability density functions of x and y. That is nothing but what? fx of x convolution fi of x. Fi of y. This is called as what? The density function of sum of two random variables. The same thing you can extend up to n random variables also. Therefore, the density function of sum of the random variables is equal to the convolution of their probability density functions. That is the definition of the density function of sum of random variables. Next definition is define central limit theorem. So what is central limit theorem states that? The central limit theorem states that the probability distribution function of sum of a large number of random variables with arbitrary distribution function approaching a Gaussian distribution function. So what does it mean? For example, I am having n number of random variables. So what are these x1, x2 and so on? It is nothing but n number of random variables. After that, sum of a large number of nothing but here n tends to infinity. Large number of random variables. And sum is nothing but I have to add all these random variables so that I am getting a new random variable. Let us say x or y, let us say. Then the probability distribution function of sum of these large number of random variables is approaching what? The distribution function of the Gaussian distribution function. That is a statement of what? Central limit theorem. So the central limit theorem, the central limit theorem states that the probability distribution function of sum of large number of random variables is approaching what? The Gaussian distribution function. The next question is define conditional distribution function of a random variable. So what is the conditional distribution function of a random variable? The probability of the event x less than or equals to x by b. So this is nothing but what? The conditional distribution function, nothing but fx of x by b. This is called as what? The conditional distribution function of a random variable. What is b here? B is nothing but it is a conditioning event. So it may be point conditioning, that may be interval conditioning. So here B is nothing but what? Conditioning event. So next one is define conditional density function of a random variable. So we have defined the conditional distribution function. Then what is the conditional density function of a random variable x? So fx of x by b is nothing but what? What is the relation between the distribution and density function? The differentiation of the distribution function gives what? The density function. Similarly, the conditional density function of the random variable x is nothing but the differentiation of the conditional distribution function of random variable x. Next one is define the marginal density function of the random variable x. So for example, if you have two random variables x and y and the joint density function of those two random variables nothing but fxy of x comma y is nothing but what? The joint probability density function. Now what you have to define? You have to define the marginal density function of x. Now what is the marginal density function of x which is represented by what? Fx of x is nothing but, how can you obtain from this joint density function? You have to integrate this joint density function over the limits minus infinity to infinity with respect to y. Then you will get the marginal density function of x. Next one is define the marginal density function of y. Similarly, how can you obtain the marginal density function of y? If you want the marginal density function of y, then you have to integrate the joint density function of the two random variables x and y with respect to what? X over the limits minus infinity comma infinity. There is nothing but what? Marginal density function of the random variable y. Next one is define expectation of a random variable. Here, expectation is nothing but, it is also called as the mean, or else it is also called as what? Statistical average. It is also called as what? Statistical average. So what is the expected value or the mean value or the average of a random variable is nothing but what? The weighted average of all the possible values of the variable. For example, if x is a random variable, then what is the expectation of that random variable? U of x is nothing but what? It is a weighted average of all the possible values of the random variable. Therefore, sigma xi into p of x equals to xi. So here sum is nothing but what? Addition. And here weight is nothing but we are multiplying this values by what weight? By what weights? Corresponding probabilities. Then it is nothing but what? The expectation of a random variable x. Now this is for what? Discrete random variable. For continuous random variable, in place of sigma, you will get the summation integration x. So e of x is equals to what? X into integration of x into fx of x into dx. This is nothing but what? Expectation of a continuous random variable, and this is the expectation of a discrete random variable. Next, define moments of a random variable. So what are the moments of a random variable? The moments of a random variable is nothing but the expected values of powers are the related functions of the random variable. So in the moments, having two types. Moments about the origin. So moments about the origin and moments about the mean. So this is nothing but what? Can define the moments about the origin, moments about the mean, nothing but these are the expectations of some powers. So here you'll get the powers. If it is moments about the origin, you'll get what? X minus 0 power n. If it is moments about the mean, nothing but what? U of x minus x bar power n. So the expected values of powers of random variable is called as what? Moments of the random variable. So today we have seen some definitions on the random variables, like what is density function, joint density function, joint distribution function, probability mass function, and then marginal density functions. And then we have seen the statistical independence of two random variables. So like that we have seen the definitions on the random variables. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.